right, good afternoon, everyone. Thank you so much for joining us for another Climate Live K-12 session for students, educators, and the public. This is a series held by the Columbia Climate School, and my name is Laurel. I'm the program manager of the K-12 and continuing education programs, and I'll be facilitating the session today. So for those of you who are unfamiliar with the Columbia Climate School or joining us for the first time, the Columbia Climate School is a newly established school at Columbia University for transdisciplinary climate research. The school marshals the university's strengths in basic and applied disciplines and expands its resources to understand climate and its impact on society, develop and inspire knowledge-based solutions, and educate future leaders for just and prosperous societies on a healthy planet. The Columbia Climate School is the first new school at Columbia in over 25 years, so we're extremely excited. And it incorporates more than 20 different centers and over 700 people who collaborate among different departments at the university, so we can better connect, amplify, and advance new areas of climate research, inquiry, and impact across Columbia and beyond. So what we're hoping to do with these Climate Lab K-12 sessions is introduce you to the interdisciplinary work through our scientific experts. These are monthly sessions that we run throughout the academic year. So for the 2022-2023 year, we're going to run through the month of June. If you would like any more information about the sessions that we've already ran or future sessions, you can visit our website that I'll put in the chat in just a moment, or you can contact us directly via email. Each week we focus on a particular topic, and each topic is directed towards a certain age range. So for today, the session is titled The Climate Symphony: How Climate Variability Impacts Global Rainfall Patterns. So climate variability plays an important role in Earth's system, and it impacts rainfall differently from year to year and from decade to decade. This presentation will focus on different modes of climate variability and their impact on rainfall, the difference between climate variability and climate change, and what happens when different modes of climate variability impact each other. So the goal of this session is to really think of the climate system as an orchestra playing a symphony. And so today we're joined by Laurel DiSera, who will be leading us in this session. Just a few logistics about Climate Live. So we have time for questions halfway through the presentation and also at the end of the presentation. We encourage you to use the Q&A box so we can monitor those questions and ensure that they get answered. And usually we have the chat box disabled, but for this special session, we really want to hear from you all. So the chat is enabled. Please use the chat to answer the questions that Laurel asks. And just so everyone knows, this session is recorded and we can send participants links to this recording after the end of today's Climate Live. So without further ado, I will pass it over to Laurel DiSera.
Good afternoon, everyone. Hopefully you can hear me and all looks good. I'm just going to share my screen now, so we are all on the same page. Hopefully gonna get it. There we go. Hopefully let me know if you can't see. But my name is, as Laurel mentioned, my name is also Laurel. I am a current PhD student at Columbia University, and we're going to be talking about the Climate Symphony today. A little bit about myself. So I'm a pretty non-traditional climate scientist. I did not study physics in my undergraduate degree. I was very interested in the math and sciences. However, I had interest in a lot of different areas. So I finished high school in Minnesota, and I then went to a smaller liberal arts undergraduate college called Concordia College in northern Minnesota, which was pretty close to the Canadian border, so pretty cold up there. Don't you know the little Minnesota accents that people are familiar with. So, and our mascot was actually a corn cob. So, that's pretty much everything that northern Minnesota is just growing corn. However, I was really interested in a lot of things. Like I mentioned, I was interested in Spanish, global Latin American studies, music, and mathematics. So this kind of shaped my time during my undergraduate. And I was actually really lucky to be able to study abroad during my undergraduate career, and I studied abroad in Argentina. And while I was there, the country experienced really dramatic impacts of rainfall. And that's what really got me interested in studying climate science. So after my degree in undergraduate, I worked for a couple of years at a nonprofit and then went to study here at Columbia University for my master's, where I did the master's in climate and society. And then I'm currently doing my PhD in earth and environmental sciences. Now, outside of school, I have a lot of interests. I like to go hiking. I spend time in Minnesota in the land of 10,000 lakes. And I like to bake, and that's my dog, Perry. So hopefully she doesn't make too much noise. But if you hear a bark, you know where that's coming from her. So that's a little bit about me. I'm happy to answer any questions that you have about college or my journey to climate science, because it's a bit abnormal compared to some of the more traditional routes. But maybe we can chat about that at the end. I will be monitoring the chat during this presentation. So when I ask questions, feel free to respond in the chat. And if you have questions for me, post them in the Q&A so that they don't get lost in the chat with all of the different things happening. So let's talk about symphonies or preparing for our symphony. And to do this, we need to talk about what a normal symphony is. So just take a second, think about some of these questions. And if you have an answer to any of them, feel free to post them in the chat. We're going to go through and talk about them, so we're a little bit more prepared to talk about what a symphony might mean in the climate sense. But you probably have all heard of a symphony or an orchestra or a band, or even a full choir. So if you have been in any of those, what do they include? Do they include instruments? Do you play an instrument? How do an orchestra or symphony or a band sound? Do they sound harmonious? How do the musicians work together? And who's the audience? Does anyone have any thoughts or examples of music? Do any of you play instruments? No, not too many. Well, I personally used to play, I do sometimes still, but I play the flute and piccolo, and I played flute and piccolo in college as well as in undergraduate. And that was really something that I participated in a lot of groups, and it took a lot of my time and a lot of my sleep, but I really enjoyed it. So if you have any thoughts on instruments or things that make your life fun in an orchestral or symphony setting, please include them in the chat. But some examples that we like to think about when we think of who makes up a symphony or an orchestra include a variety of instruments. For example, a cello in an orchestra or a flute in a band or orchestra. You have timpani, drums, you have trumpets, cornets, trombones, saxophones, even if you're in a normal concert band. But sometimes you can have singers, depending on if you're playing Handel's Messiah, for example, or other pieces that might require singing. But the one thing that's always constant is the director. Most groups, whether they're big or small, like to have somebody that leads them. And that's really important in keeping people on the same page. So a symphony typically has different types of sounds. They can be harmonious, but sometimes they can be dissonant. And we often need these dissonant parts to make the harmonious parts more worthwhile, right? You have to have the ups and downs to be able to appreciate some of the nice, very triumphant parts of music. But some parts can be a little weird and might make you uncomfortable or make you nervous or make you scared or sad. But that's the beauty of music, and something that we also will think about when we're thinking about the climate system. And then we also think about how the different musicians work together, how they listen to each other. They keep tempo maybe with a metronome, or how they respond to their director. Maybe they're watching their director's movements, looking for different crescendos or cues that might encourage them to do something different than what they see on the page, for example. So this is a way that the musicians can play together and work as a team to create the sound of the music that is expected by the director, or how the music was written to begin with. But then we have the other flip side. We have all of these people like you who are coming to this as an audience. All symphonies or orchestras usually have concerts where they perform, and people come from all over the place, from different backgrounds and different life experiences, to listen to this music. Often they'll be fulfilled. They might be moved emotionally. They may cry. They might be very joyful when they hear this music, depending on what's played. They'll probably learn something and potentially grow in their music endeavors, whether they're just listening or they're playing when they listen to this music. So the audience in a symphony setting, in a concert setting, is often really important to think about as well. So now that we've talked a little bit about what a symphony is in a way that you may have heard about it before, let's take a little bit of time to think about what our climate symphony might be. So we have a variety of things going on here that are all moving and very distracting. We have a simulation of clouds on the left. And the blue clouds are actually special clouds that are formed in different parts of the atmosphere due to different chemicals. But you can just kind of see how the clouds move generally around the world. In the top right corner here, we have winds. If you look really closely, those little green areas are actually moving and showing different wind patterns around the earth. And if you look below on the bottom, you see changing sea surface temperatures. And all of these components are influenced by the Earth itself and by different members of the climate symphony. So we're going to talk about a few of the different members of the climate symphony. And then we're going to move on to discuss a little bit about how climate change is going to impact our climate symphony. So first, discussing climate variability and then climate change. So some of the members. Our members of our climate symphony don't really play instruments, so to speak. We kind of refer to them on terms of time scale, or how fast or quickly they move over a long period of time. So kind of, instead of thinking about trying to equate them to one exact instrument, we can think of maybe how they can work together. So you all have probably kept track of this. You have the app on your phone that gives you the weather from day to day. But here are just some examples of what we as climate scientists consider one of our symphony members, which is the most rapidly changing type of weather, or type of climate symphony member, which is weather. There are tornadoes, there are thunderstorms that bring rain, there are clear sunny days, and there are also blizzards. Granted, if we all live in the New York area, we know that there haven't been too many blizzards down towards Manhattan. Does anyone have any other ideas of other types of weather that we may experience other than snow and rain and sun? And feel free to post them in the chat. There's like literally no wrong answers. Right now in New York, it is sunny. I think it's mostly clear sky. I haven't been outside for most of the day, but it looks like it is a nice day out. Yesterday was really windy. I'm not sure if anyone was around or walking outside and experienced that, but it was quite windy out, blowing away things that I saw. So weather is moving pretty quickly. We see that weather patterns change from day to day, right? You may have seen something like this on the news if you ever watch the news, maybe a map that looked kind of like this, that looks at low and high pressure systems. And a map similar like this helps to inform weathermen and weatherwomen on the television, and help them explain to us when we might be experiencing rainfall, for example, or a thunderstorm as it progresses over the United States. And we've gotten better with forecasting from what we used to be. But probably on your app on your phone, you might not want to trust something that's more than 5 days out, for example, because it changes, right? So scientists and meteorologists are still working on getting our forecasting to be more up to speed and more useful for people to be able to plan picnics in the park for next weekend, for example, or going to a particular sporting event that's outside. So all of this is really important for us to understand for the day to day. So this is our first Climate Symphony member. Our second member, you're probably also all familiar with. This is our seasonal cycle. From spring to summer to fall to winter, we see changes in our climate. And this is primarily due to how our Earth is positioned and moves around the sun, which part of the Earth is experiencing more direct sunlight or less direct sunlight during the year. And that will influence our summers and winters, and that is opposite in the Southern Hemisphere. We can talk more about that later if you have questions, but it is primarily driven by the sun. And the sun is also really important because it heats different parts of the Earth as it moves throughout the year. And this impacts how our rainfall changes. So from season to season, we're going to see rainfall changing across the globe. If we look at this, so this is an image that we can see of rainfall on the Earth. On the left side here is Africa that you can see, and here is Europe and Asia and the Pacific Oceans in the middle, and then we have North America. In this top panel, we are looking in January, and the second panel on the bottom, we're looking in July. And the dark green colors are showing where we have the most rainfall. We can see in the winter, all of the rainfall most of it seems to be south of the equator, and some of it appears to be north of the equator. And this has to do with where the sun is and how warm the water is that the sun is shining on. So our seasonal cycle and how closely we are facing the sun, for example, can impact where our rainfall changes, where it can be stronger or it can be weaker. So the sun and our cycle around the sun is another really key important player in our climate symphony. And it changes, obviously we're going to have a full completion of it every 1 year, but you're going to see changes every 3 to 4 months or so when you're potentially closer to the equator, this like bold red line here. So these are weather and our seasonal cycle are probably most common and what you probably learned about in school prior to this presentation. But we're going to talk about a few other Climate Symphony members that might not be as familiar to you. So one of the other Climate Symphony members that you are just going to meet is called the Madden-Julian Oscillation. And the Madden-Julian Oscillation is essentially this, think of, if you're looking at this diagram here, it's like really stormy weather over a particular region that then forms clouds and it rains. And then we have dry air that sinks down because it has no more water, and creates dry, sunny areas in a different part of the world. And these stormy, wet areas can cause major flooding. And something that scientists really have to keep an eye on because they need to be able to warn governments and other leaders and decision makers about potential threats to communities. But the crazy thing about the Madden-Julian Oscillation is that it actually moves. So if you look at these cool globe images, you can see that there are these really kind of brownish areas. Just kind of ignore the purple parts because we won't talk about that today, but there's the brown areas and the teal areas. And the brown areas represent dryness and the teal areas represent rain. So you can see this is Australia and then this is South America. So it's just kind of showing two different sides of the globe. And you can see that this rainfall kind of moves towards the east, and it is both followed and ahead of, or is behind, I guess, a dry area. And this is the probably one of the more key important things about the Madden-Julian oscillation is it moves rapidly. So we have rainfall events that are moving every 30 to 60 days. And this isn't something that you can find on your weather app on your phone. This is something that we're still working on getting incorporated into our weather forecasts. So it's one of the new and kind of cutting edge things that scientists are looking at today. And like I said before, if you have any questions on anything or you want me to clarify, feel free to drop any questions into the Q&A and I'll get to them when we get done talking about our different climate drivers or our Symphony members, I guess we could say. This one, however, you may have all heard of. This different type of climate symphony member is called El Nino Southern Oscillation. And it occurs on a time scale of every 3 to 7 years. So we're going to dig into El Nino Southern Oscillation because I think a lot of people have heard about it, but may not know what it is. So in El Nino Southern Oscillation, our main area of focus is the Pacific Ocean. So we can see here on the left side, you can see like the northern little tip of Australia and Southeast Asia. And on the right side, we can see part of Mexico into Central America and South America. Well, the western part of South America. And we see that it appears to be like 3 different types of El Nino Southern Oscillation. We see something with really red color here, which when we look at the scale bar on the right, we can see that this is temperature anomaly, which means if we take the normal temperature and we remove it from the sea surface, this would be the anomaly or what's left over. So we see that there's some really warm temperature here in the ocean. In the El Nino state, there's a neutral state, which has some warm and some cool, but nothing very strong. And then there's a La Nina state that has very cool temperatures. And these are all driven by a variety of mechanisms that we're going to talk about step by step to kind of help you see how these are formed and what they can do. There we go. So to start off with, El Nino Southern Oscillation has, like I mentioned, 3 different phases, and we're going to start with the neutral case. So in the neutral case, remember we talked about how the winds move and there is often rainfall that happens in a particular region and then drying. Well, this is very similar to the Madden-Julian oscillation, but on a different time scale and a much larger scale in general. So in the neutral time, when there's no El Nino or no La Nina event, we have trade winds that are pushing warm air and warm water over towards Australia, which then form clouds. We have convection that forms, rising air, and then we have dry air that moves over towards North America, descends over this cool region. So it's kind of a big cycle. And this is what we call like the normal or the neutral state of El Nino. And we can see if we look under the water, we can see here in the small panel what is exactly going on. So if we think this top part of this panel is the surface, and the bottom of this panel is down several hundred feet into the water. We have this region of warm water, which we see here, and we see over here in the East or Western Pacific. We see this cool area here, which we see here in the Eastern Pacific. Then we have this thing called the equatorial thermocline, which is essentially just like this layer in the water where you pass under it. You pass under it or above it, and the temperature changes really quickly. So you might have warmer waters above, which you can kind of see here. It's like a light blue, but below it, it's like very cold. And this changing of the thermocline height is one of the key indicators to El Nino Southern Oscillation. And so there are there are two other forms of El Nino Southern Oscillation besides the neutral. There is La Nina, which I mentioned before, where we have a really cool section of water here over a big part of the Pacific Ocean. And we have really warm water over by Australia and Southeast Asia, and a lot of rainfall that happens here. So a lot of people consider La Nina to be like a strengthening of the neutral conditions, because you have really cold water that really just gets pushed farther over than it does during neutral years, but a very similar mechanism. But we see in La Nina years, for example, up here at the thermocline, that you have a lot more cool water that's being pushed over towards Australia than you do during the neutral years. And finally, we have El Nino Southern Oscillation, which has kind of a reversed pattern than what we see in La Nina, starting with the warm water in the Central Pacific versus having the cool water in the in the Eastern Pacific, and having more cool water over Australia and having it be quite dry. And our rainfall actually gets pushed over into the Central Pacific. And so we have less rain over Australia and more rain over Central America, for example. We also see the trade winds also being pushed in different directions. We have weak trade winds here in the warm water, and even some wind coming from the Australia area. And you might think that this seems kind of like hard to, I think, sorry for 1 second. Okay, I'm back. Sorry for the dog interruption. But when I started learning about El Nino Southern Oscillation, I was like so confused about how anyone would be able to figure this out. You know, like this all happens over the Pacific Ocean. So how do people figure this out? And what I was really surprised to learn about was that it really was discovered by farmers fishermen who farmed the ocean, that discovered El Nino Southern Oscillation, because they were like trying to catch fish. But when the water temperature turns really warm or really cold, this can impact how many fish are able to thrive off the coast of Peru. And so these El Nino events will happen around December. And so the Peruvian fishers realized around the Christian holiday Christmas that their fishing patterns were changing. And so they named El Nino Southern Oscillation El Nino, because of the fact that El Nino stands for the child, which represented Jesus Christ, the Christ child in Christianity. So I just think that that's really cool that this was known about and studied well before any climate scientists came along to learn about it. So here is an animation that I showed earlier, but now you can kind of see and visualize what this warming sea surface temperature looks like during El Nino years and then La Nina years, as you see like this warm band of water here turn into a cool band of water in 2016. 2015 was one of the largest El Nino events that we have ever experienced on Earth, and actually happened to be the event that happened when I was studying abroad in Argentina, and major rainfall happened there because of this event. So it was kind of cool. And there's a way that El Nino Southern Oscillation is not just like impactful in the Pacific Ocean, but there's a way for us to understand how it impacts the entire globe. And we can see that in this image here. We can see during El Nino years, it's drier in this brown area in some places than others, and wetter in some places than others, and in different parts of the year. So scientists study this, and they understand, are getting better at understanding how to incorporate these forecasts of El Nino and La Nina into their system so that we can better prepare farmers and even civilians everywhere for things that El Nino can bring. And some are good. Sometimes it can bring prosperous crop growing seasons to some regions, but sometimes it can be a little detrimental and quite dangerous, as, for example, fires, which were seen in Australia during large El Nino events, and also flooding in some regions as well. And so El Nino is another one of our climate symphony members that happens on a little bit longer time scale of 3 to 7 years, but it has a lot of impact around the globe compared to some of the others that we've looked at. And finally, 2 other climate symphony members. I mean, there are a lot of climate symphony members. You know that there are more than I listed for the orchestra example, but these are just a few that I thought would be good examples. So the Pacific Decadal Oscillation is here on the right, and this also has to do with the temperatures in the Pacific Ocean, but moving on a much slower time scale. We're talking about 10 or more years that these sea surface temperatures will move and modulate, so very slow. But it has a big impact on agriculture, surprisingly. These changes in the Pacific Ocean can impact grape growth in the United States and France, some of the largest grape growing producing regions in the world, as well as the Atlantic multi-decadal oscillation, which has to do with the sea surface changes of temperature in the Atlantic Ocean. And this can impact growing corn in the United States. So these changes in ocean basins that may seem far away from, for example, the Midwest, can actually have a pretty big impact on the crops that we grow and what that means for our food security all over the world, which is kind of a big deal. So when we think about all of our climate symphony members, we see that they all happen on different time scales. We have very quick time scales like weather. We have some that are a bit longer, and then others that are really long or somewhere in between, right? And understanding how they all work together is really important, and is actually what I do my research on every day, trying to understand when the Madden Julian oscillation, for example, is over Australia and we have an El Nino event, what does that mean for rainfall? How does that impact the people that are living there? What does that mean for their livelihoods? And this is something really important, and we'll talk a little bit about it later. But to bring it back to a symphony example, and this is really what I think is really a good visualization to think about, is we have a piece of music, for example, and we can assign different modes of these climate symphony members or climate drivers, and see how they all kind of work together. We have our seasonal, or our something changing every 3 to 4 months, and this might be our melody that we're experiencing, our fall, our winter, our summer. But we also have weather, which is kind of crazy and sporadic. It's like every other day that it's changing and it's moving very quickly. And that might be what we find in the violin and clarinet part, for example. But we also have some slower moving drivers and faster, depending, but more sporadic, that also contribute to this symphony of the climate. And when we play them together, we might get very beautiful harmonies when we see a nice, beautiful sunny day or a season with fewer hurricanes, for example. But when we experience dissonance in the music or in the climate system, we might experience an El Nino event that's compounding with other climate symphony members to create flooding or to create drought that can really be impactful on society. So I'll take a little bit of a pause here to see if anyone has any questions. I don't know if there is anything in the Q&A.
Laurel, I haven't seen any questions come in, but I encourage you all to include them now if you do have any questions at this time.
And I can answer any questions later too. It's just kind of what you're interested in learning. If you have like certain questions, it just depends on, I can't necessarily tell you what part represents each instrument all the time, but they do change over time. So yeah. So next I thought like it's important to also discuss how climate change impacts the climate symphony, because this is something climate change and climate variability are often discussed, but sometimes not together. And it's really important to understand how climate variability is kind of happening underneath climate change, because some events that happen in climate change or in climate variability might set off bells ringing saying, oh, climate change is causing such and such thing to happen, when really climate variability is behind it. And sometimes climate change is impacting climate variability, but it's something that we really need to consider and think hard about when we are attributing specific events to climate change. So I'm not sure how familiar everyone is with the greenhouse effect and its real contribution to climate change. So I thought I would just talk a little bit about it. If you have any questions, we can talk more. But just to give a little overview, I'm not sure if any of you have been in a greenhouse. If you have, that's awesome. Greenhouses are really fun. They're essentially like a building. I'm not sure. I know some of the buildings in New York City have greenhouses on top of them. I've seen. I think a Columbia building does, and others I'm sure do, but we probably can't see because they're too tall. But in a lot of suburban and rural areas, people do have greenhouses. Greenhouses are a house essentially that has a structure, but not hard walls. So there are no bricks that make up the house. There's no concrete or sheetrock or plywood that make up the walls of the house. It's a transparent, can be some sort of film, it can be plastic, but essentially the goal of this greenhouse is to trap heat. So the heat can come in through the clear walls or roofs and get trapped inside. And this allows for us to grow things. Even in the winter, we can grow plants on the inside because we have this blanket of protection. Here, in this case, it's plastic that can allow for us to trap the heat and grow, whether it be produce or whatever we need during the winter. And a greenhouse is essentially like the same effect that the earth is experiencing, right? So we have gases in our atmosphere that protect us from losing all of our heat to outer space. This is not the same for many of our other fellow planets, such as Mars or Venus. They have lost their atmosphere. So they're very, very cold at the surface. And this is a problem for them, obviously, and we can't go there and live there because they don't have anything to protect us. And we can't give them back an atmosphere, which is also a major issue. So that's, I'm not sure about, I'm not an expert on colonizing Mars, but I think it might be pretty difficult. So the greenhouse effect is made up of gases, like I mentioned, that kind of blanket and cover our Earth. So a few of the gases that are found within the greenhouse effect are carbon dioxide, methane, water vapor, and ozone. So just to give a little bit of background to these gases, I just have a couple pictures. We have carbon dioxide, which I'm sure you all know comes from cars, it comes from factories, anything that works with fossil fuels, coal, anything really from within the earth, right? And this is something that we can control, that we have been pumping into the atmosphere. We have methane, which we also generally control. Methane can come from a variety of sources. Probably the most well-known is from cows. When cows process their food and then they release gas, specifically from belching, they released methane into the atmosphere. Fun fact, I recently learned that scientists are working on implementing in Australia a food additive for cow food, that it's like some sort of algae that they can add to a cow's food that will reduce the methane that the cows produce in their stomachs and then release into the atmosphere. So really cool things. If you want to learn more about that, I can direct you to some information on that. So that's, I know there are other initiatives happening in other places, But it seems like it's a really interesting tool that people are using and hopefully can implement more widely. So methane is actually more potent of a greenhouse gas than carbon dioxide. So it's much worse in the atmosphere, much worse for harboring heat. However, it is much less abundant, which we're really lucky for. If there was a lot more of it, we would be in really big trouble. The third greenhouse gas is water vapor, which I'm sure you're all familiar with. When you heat up water on the stove, you're going to have boiling water, which then releases water into the atmosphere. And you might do this to add humidity to your house when it's really dry. And so you're not constantly drinking water or having really dry skin. But water vapor is present in our atmosphere, and it has been there since the beginning of Earth. And water vapor is really important at maintaining Earth's habitability and keeping us warm within the greenhouse effect of how it was before we altered it with carbon dioxide. And I'm sure you all have heard and talked about the water cycle, which, we have this evaporation forming into clouds and then rain. So water vapor is like a crucial part of the water cycle, and also something that contributes greatly to our well-being and staying warm here on Earth. And then finally, ozone. Really don't get involved with ozone. Ozone is very dangerous for you. If you're ever in a region where they're like high ozone levels, you need to get out of there. But ozone is essentially created through a chemical process in the atmosphere when we have a release of carbon dioxide, for example. In regions that have carbon dioxide, there are little atmospheric reactions that happen, and ozone can be created. So these are kind of the four most well-known greenhouse gases. There are many others, but they have a lot smaller concentration in the atmosphere and are a lot, they might be very potent, but they just are a lot fewer and far between when you look at all of the atmosphere, or all the molecules in the atmosphere. There are other molecules. These are specifically greenhouse gases, but you have nitrogen and other molecules floating around too. And greenhouse gases, as I mentioned before, are kind of our doing. We are putting them into the atmosphere, and we are really impacting temperature. So here is just a plot that is looking at carbon dioxide concentration that we see here on the y-axis, and on the x-axis we see time. So it starts around 1700, and we see carbon dioxide concentrations increasing, but more so increasing most rapidly after 1960. If you think about maybe why we started increasing in 1850, maybe the Industrial Revolution rings a bell, and you can say, okay, maybe that's when we started emitting, but you can see there's a pretty slow increase. And then all of a sudden after 1960, we see this massive uptake in release of carbon dioxide. And this has to do with a variety of reasons, which we can discuss at further length later if you're interested. But we've been tracking this information for a long time. This kind of darker part has been monitored at Mauna Loa, their big observatory on the Big Island of Hawaii. But before, they were using ice core data, which if you have questions, I can also discuss about afterwards, because ice cores are really cool. And if we look at that here, we can see that since 1880, so this is a little bit short of a time scale, but if we look where we started to see an increase in the last plot in 1960, we can see this increase as well. This is looking at just temperature from a variety of different temperature monitoring devices or models. And this is looking at temperature anomaly again. So if we were to remove the average temperature, the annual average temperature, we would be left with some sort of leftover. And we see that this leftover has been increasing pretty rapidly since 2020. And we can see this visualized here as we get warmer and warmer and warmer. Which actually is quite terrifying. You can see that the Arctic is warming very rapidly compared to many parts of the world. But it is very impactful. So the question comes to, how does climate change impact our climate symphony? Well, climate change, if you want to think of it in like the musical sense, and if you're not familiar with this term, that's okay, but you could think of the climate symphony being modulated by climate change to another key, for example, or impacting how fast the tempo is of the music. How quickly are we changing our seasons, for example? The spring came awfully fast in New York this year, and that might have to do with some climate variability, but it also might have to do with climate change. And I'm sure there are many scientists working to try to publish that information right now as we speak. But this can also impact extreme drought. It can impact hurricanes and intensity and frequency of hurricanes. It can impact where our rainfall is going to be changing, how we're going to be changing our rainfall around the equator, and if more places are going to be getting more rainfall than others, and some places might be experiencing a drying overall. And then all of this has interface with the ocean, right? So as we get warmer and warmer, the ocean is going to have to take up some of our heat. And this might it might impact how some of our longer scale climate variability or our climate symphony members behave. How are sea surface temperatures going to impact El Nino? Or how are they going to impact the Pacific Decadal Oscillation? And these are some questions we're still working on today to try to understand. But all of this is interesting in the climate sense, but really we want to think about the audience of the climate symphony. Who's being impacted by our climate symphony? How is this changing the way that we live our lives, right? So, I mean, first and foremost, before any humans get mentioned, there's a very diverse animal population, species of all different kinds that are being impacted by climate change, ranging from polar bears to aquatic species that I've never heard of in my life, but people are studying with great interest to try to understand how ocean communities and different forms of biodiversity and life are being impacted by climate change. But on top of all this, climate change also impacts us and people's all kinds of jobs. Farmers obviously are going to be impacted in the fields, as well as construction workers. Teachers and professors are going to be impacted. Firefighters for fires, for example, forest fires or wildfires. Pilots, depending on how the atmosphere responds to climate change, this might impact aviation. Nurses and surgeons even. I was talking to someone recently that is a surgeon who was saying that transport of surgical equipment is being impacted by climate change because of the fact that, for example, extreme heat or extreme rain is impacting ability for the transport or the supply chain of goods. Which I thought was really interesting and something that I had not even thought of, and that's impacting how many surgeries can be done or the quality of surgery. So this is going to impact everyone, and it is impacting people as it is. And so we are all the audience of the climate symphony and how it is changing. And this is important for a variety of reasons, like I mentioned before, whether that be for farming in the United States or anywhere in the world, but also for flooding and flood risk from hurricanes or sea level rise. And this is something that our leaders have been working on for a long time. More recently with recent infrastructure and legislation that has been passed. So that's, at least pretty encouraging from the US perspective as of late. But I also wanted to mention how this is also impacting people of different communities based on previous policies that have been made in the United States, for example, and how it's impacting folks of different races. And I feel like I almost see this daily in the news, and how redlining, for example, or other forms of segregation that happened in the 1930s or before are impacting people differently. So redlining, just as a brief introduction, and if you have questions, we're almost at the end and I can explain more, but redlining was essentially done in the United States in many large cities in the 1930s and effectively pushed communities of color, specifically Black communities in particular neighborhoods, and gave their property values lower values than primarily white neighborhoods. And a lot of these communities that are redlined or red colored, as you can see here, have struggled with environmental related concerns. They have been exposed more severely to pollution and unjustly. I feel like I'm on The Guardian every day reading about different things that people are coming and studying and finding that have been impacted by redlining in the history of the United States. So this is something that researchers are working on, trying to understand how to be more environmentally and climate just when it comes to actions that we're moving forward. And one example in the Harlem area that you may know or understand is this is a picture of New York City looking at surface temperature. And we can see that the cooler areas are blue here and the warmer areas are red. And when you're on the east side, for example, you can see that it's maybe not too cool or not too warm. But if you move up into Harlem, it gets much warmer. And so understanding how we can study and implement climate change adaptation and mitigation in a way that's climate and environmentally just is really important and really harkens back for us to better understand how climate change is happening and how climate variability or our climate symphony is also changing and what that means for all of us and our future on this earth. So that's what I have today. I'm so glad that you were able to join and learn a little bit about the Climate Symphony and about some changes with the climate and what that means for us in our future. If you have any questions, let me know. Otherwise, yeah, it was great chatting with everyone and hopefully your today's Wednesday is going well.
Thank you so much, Laurel. This was great. I love just thinking about the climate, which can be really complex. There's so many variables, so many drivers in the form of a symphony, because I feel like it's so much more tangible when you think about it in that way. So for the folks that we have live, if you do have any questions for Laurel, please put them in the Q&A. We haven't received any yet. And I just want to remind everyone that I put the link for the Climate Live K-12 website in the chat. So if you're interested in looking at any of the past recordings, you can feel free to find them on that page. Any future sessions that you want to RSVP to, you can do that there as well. And if you do have any questions for myself, you can email me at learn@climate.columbia.edu, and I'd be happy to answer any questions you have or connect you to any of the experts. All right, Laurel, I don't see any questions in the chat, but thank you so much for spending the last hour with us. This was really fun, and I think I can speak for everyone when I say I think we all really enjoyed it.
Thanks so much. Yeah, it was a great time. If you have any questions, feel free to reach out. My email is there. Be happy to chat with anyone or any groups if you're interested in learning more.
Amazing. All right. Bye, everyone. Have a great afternoon.
Thank you.